So hi and hello there. Welcome to the new video, and in this particular video we are going to design, simulate and implement one circuit diagram which will check if my battery it is in charge condition or it is in discharge condition. Okay, so this particular circuit will only work for 9 volt of battery. So that's why you can clearly see over here I had given the name of this project as 9 volt battery indicator circuit diagram. Okay, so at the end of this particular video you would be in this situation to implement this particular circuit. So hello everyone, I had made one circuit which will actually check if my battery it is in charge condition or it is in discharge condition. So if the battery it is in charge condition, so only the green LED will glow, okay, and if it is in discharge condition, so only this particular orange LED will glow, okay. So let me connect this particular battery to the circuit. If this particular battery will be in charge condition, so only the green LED will glow. Solid. So you can clearly see that only green LED it is glowing, which indicates that my battery it is in charge condition. So let's connect this particular battery to the multimeter and let's check if this particular battery it is in charge condition or it is in discharge condition. Right. So you can clearly see that my battery it is in charge condition as it is providing 9 volts. Right. So now what I will do, I will just connect this particular battery to check if it is in charge or it is in discharge condition. Alright, so you can clearly see that this particular green LED it is not glowing, which indicates that this particular battery it is in discharge condition. So let me just see over here. Yeah, you can clearly see that this particular battery it is in discharge condition. So if you want to understand this particular concept, you make sure to subscribe my YouTube channel. Alright, so now we are going to see the rough idea or the basic understanding of this particular project with the help of one block diagram. Okay, so the basic agenda of this particular circuit is to indicate or is to provide that my circuit let my battery whether it is in charge condition or it is in discharge condition, right? So for that I will require two batteries. Out of those two batteries, one would be in the charge condition, whereas the second battery it would be in discharge condition. Okay, so what I will do, I will just go with this particular first assumption that whatever the battery that I'm connecting to this particular circuit it is in charge condition. Okay, so these are the certain blocks of this particular circuit. I will come to this particular block after some time. Okay, first we'll just understand basic understanding. Okay, we'll just understand the basic understanding of this particular circuit, like how exactly things will work when we are going to design it. Okay, so let's assume if I'm connecting a charge battery to this particular system 1, so this system 1 will give certain output, and based on that particular output I will be able to go on whether my battery it is in charge condition. Okay, let's suppose if I'm connecting a discharge battery, okay, then system 1 will give certain different output. That particular output has to be passed from this particular system 2, and then this system 2 will generate certain output. Okay, so whatever the output that is generated by that particular system 2, that will indicate me that whatever the battery that I had connected it is in discharge condition. Okay, I will come to this particular point, or rather we will come to this particular block diagram when we are designing each and every block step by step. Okay, so first of all I will just go with this block, that is charge battery system 1 and output. Okay, so let me proceed further. Alright, so since we are designing a circuit for 9 volt of battery, okay, and let's assume this particular battery it is in charge condition. So this is the assumption that we have to make. This is in charge condition, okay, and it is able to deliver 9 volts. Okay, it is able to deliver 9 volts. Okay, since it is able to deliver 9 volts, so you can clearly see if I connect this particular battery directly to the output, that means over here I had clearly mentioned over here that LED. Okay, I want to check if this particular battery it is in charge condition or it is in discharge condition, so that I'm able to check with this particular LED, right? Okay, so let's assume if I'm connecting this particular battery directly to this particular LED, then what is going to happen? If I'm connecting this particular battery directly to this particular LED, then of course this particular LED would burn out completely. That means what? I cannot connect this particular 9 volt of battery directly to this particular LED, right? I hope you are getting this particular point, right? Why? Because whatever the voltage that an LED requires, it should be less than or equal to 5 volts. Okay, so the maximum voltage that an LED can bear, it is roughly around, so the maximum voltage that an LED can bear or that an LED can suffer, it is less than equal to 5 volt. Okay, it is less than equal to 5 volt. So if you give a certain voltage which is greater than 5 volt, then this particular LED will burn out completely. And in this particular scenario we are directly connecting 9 volt of battery to LED, so obviously the LED will burn out completely and then it would be of no use, right? I hope you are getting this particular point. Great. So basically we need one system in between which can actually handle this particular 9 volts, and at the same time it will provide certain voltage that would be less than 5 volt. I hope you are getting this particular point, what I want to convey to you all guys. So basically I want to design one system in between which will act as a mediocre, okay, which will act as a mediocre. Let me take this particular card. Okay, let's assume this is system 1. Okay, so what this system 1 will do, it will take this particular 9 volts. Okay, it will take this particular 9 volts from this particular battery. That means whatever the voltage that is being delivered by this particular battery, in our case this particular battery is of 9 volts, so it should be able to take this particular 9 volt, and at the same time it should be able to deliver the voltage which is less than 5 volts. So let's assume this particular voltage is less than 5 volts, okay, or it is equivalent to 5 volts, it's one and the same, okay, to this particular LED. So what component or what device you would be using in between so that it would be able to decrease the voltage, and obviously if you are decreasing the voltage, so it should be able to decrease the current as well. Why? Because LED, the maximum current that an LED can bear, it is roughly around 20 to 30 milli. Obviously if you are increasing the current, so obviously then the LED will burn out. So at the same time we have to look upon two parameters, that is voltage and current. So basically we do not want to go beyond 20 milli, and we also at the same time we do not want to extend the voltage above 5 volts. So we have to take two parameters into account while designing this particular circuit, or rather while while using that particular component. Okay, so just try to think, just it's my request to you, please pause this particular video and try to think in your mind what particular component we can use in between, or what particular component can act as a mediocre which can take 9 volt and deliver 5 volts at the output side. Okay, just pause this video and try to think in your mind. Alright, so I hope you tried your best. Now it's my time to explain you this particular thing. Alright, so the component that we are going to use, it is transistor or normal BJT, that is BC547. So to design this particular system, let me change the color. So to design this particular system, the component that we are going to use, it is a BJT BC547. BJT, normal BJT transistor BC547, that is BC547. Great. Alright, so I hope you understood everything up till here. Now that's the different scenario how we are going to design this particular system, or rather how we are going to design this particular circuit. Okay, so this is what I wanted to convey to you all guys. See, this is a 9 volt of battery. I need to pass through this particular transistor so that this particular transistor would be able to decrease the voltage and current. Okay, see, I'm not telling that I'm providing this particular 9 volt directly to the base of transistor. I'm not telling this. Okay, so basically there is one circuit, okay, and in that particular circuit there is one BJT, okay, and that particular BJT, it is able to control all of these particular things. Okay, so long story short, let me just give you a idea. Basically we are going to operate this BJT as a switch. So basically the application of this particular BJT is to get operated as a switch. So basically over here we are operating BJT as a switch. So let me write over here BJT as a switch. Okay, BJT as a switch. This would be the basic operation of this particular BJT, right? Okay, so now what I will do, I will move to the designing part. We will start with the designing part. So let me move further. Okay, so alright, so you can clearly see this is how we are going to design the system 1. Okay, I know this would sound little crazy to you as of now. Okay, but we will try to understand each and every thing in depth. Okay, so since we had a deal with BJT, I mean, I hope you might have gone through my courses, and in one of the courses we had deal BJT in great depth, right? So now we have a basic understanding about BJT, is that to switch on the BJT, or rather to operate BJT in the saturation region, the voltage drop across the base emitter junction, okay, so the voltage drop across the base emitter junction should be equivalent to, or it should be greater than or equal to 0.7 volt. Okay, it should be greater than or equal to 0.7 volt. If I am providing a voltage greater than or equal to 0.7 volt, so this particular transistor would be, or this particular BJT, it would be in the switch on condition. That means it will act as a closed switch, or rather it will be operating in the saturation region. Okay, the meaning is same, right? Okay, just the thing is that we need to provide the base emitter voltage greater than or equal to 0.7 volt. So this is the basic idea. All right, so let's assume the battery that I had connected, it is charged, right? So basically I would be connecting this particular battery over here. So you can clearly see over here, this particular battery I'm connecting over here. Let me take different color. All right, so whatever the battery that I need to connect or that I need to check whether my battery it is in charge condition or it is in discharge condition, I will connect the positive terminal of this particular battery over here and negative terminal of this particular battery over here. Okay, I hope you are getting this particular point. Okay, and for this particular instant, we assume that whatever the battery that we are going to connect to this particular system one, it is in charge condition. That means it is able to provide 9 volt. Okay, I hope you are getting this particular point. Again, I am repeating this particular point. See, battery has two terminals, positive and negative. So the positive terminal we are going to connect over here, and the negative terminal we are going to connect over here. Okay, and for instance, we are assuming that whatever the battery that we are connecting, it is in charge condition. That means it is delivering 9 volts. Okay, it is delivering 9 volts. Okay, great. All right, so we all know that to operate BJT as a switch, or rather to operate BJT in the saturation region, we need to provide VBE greater than equal to 0.7 volt. So we just, as of now, we just know these two parameters. That means VCC is equivalent to 9 volt, and to operate BJT in the saturation region, or rather to operate BJT as a closed switch, we need to keep base emitter voltage greater than or equal to 0.7 volts. Great. So can I design this particular circuit in this way such that, see, if the battery it is in charge condition and the battery it is of 9 volt. Okay, if the battery is of 9 volt, and as soon as I connect this particular battery over here and here, that means the positive terminal of battery I am connecting over here and negative terminal of battery I am connecting over here, and as soon as I connect this particular battery over here, so I will be getting the drop of around 0.7 volt across the base emitter junction. Okay, again I am repeating this particular point. See, can I design this particular circuit in this way such that as soon as I connect this 9 volt of battery, the voltage drop across the base emitter junction would be around 0.7 volt. Okay, I hope you are getting my point. So what I want is that, see, when VCC, when I will connect, when I connect 9 volt of battery, or rather battery which is in charge condition, it is delivering 9 volt. Okay, and when I connect 9 volt to the system one, right? So this is like a system one. See, this whole of the thing, it is like a system one. Let me take this particular dotted lines. Okay, and which color should I use? I think I will go with this one. All right, so this particular thing, see, this one, these are the terminals of battery. So this particular thing, see, this one, this is your system one. Okay, this is your system one. Let me just write over here. This is my system one. Okay, so this is my system one. System one. Okay, this is my system one. So when I connect 9 volt to system one, when I connect 9 volt to system one, okay, at that particular time the voltage drop across base emitter junction should be around 0.7 volt. So VBE should be, okay, you can clearly see VBE I represented over here. So at that particular time VBE should be equivalent to equivalent to 0.7 volt. Roughly it should be around 0.7 volt. It's fine even if gets increases. That means if you are getting VBE as around 0.8 volts. Okay, but the most important thing that you should remember over here is that I'm using BC547 transistor. Why? Because it has capacity to that it can pass a current, and that means current IC roughly around 100 milliampere. Okay, that means this is a very huge amount of current when you are dealing with electronics. I know it is in milliamperes, but still when you are dealing with electronics, that too especially with transistors, so it's a huge current, 100 milliamperes. But for this particular application we just require a current which is less than 2 milliampere, right? And at the same time the maximum voltage that a BJT can handle, it is around, that means BC547, it can go beyond 15 volts at some times as well, right? So but for our application we require 9 volts, right? So that's why we are using BC547. Okay, if you want you can go with MOSFETs and JFETs as well, that's up to you. But since this particular application requires this voltage, I mean this amount of voltage at 9 volt and 20 milliampere, so that's why I'm using BJT, that is BC547. Okay, I hope you are getting this particular point, that why I'm using BC547. Any which ways we'll come to this particular point. When I connect 9 volt to the system 1, so what I want or what I desire is that to the base emitter junction I will get I should get the voltages around 0.7 volts. Okay, I should get the voltage of around 0.7 volt. That means what? Let me just highlight this particular point. That means I want that my BJT should be operated. Just a second. Let me use different color. Alright. So what I want is that my BJT should be operated in the what? In the saturation region over here. So sorry. Alright. So with this particular scenario, what I want is that my BJT should operate in the saturation region. BJT should operate in saturation region, I'm writing it in short, saturation region, or rather it should act as a closed switch. Okay, it should act as a closed switch. This is what I want, or this is what I desire, right? What I desire is that when I connect 9 volt over here, you can clearly see 9 volt of battery across this particular system 1. So at that particular time, my BJT should be operated in the closed switch. And why it should be operated in the closed switch? Because see, if this particular BJT operates in the closed switch, okay, let's assume I'm connecting these two terminals. So you can clearly see maximum current would be flowing from the collector to emitter junction, and therefore this particular LED will glow. And since this particular LED, if it is in the switch on condition, that means if it is able to switch on, that means what? It will indicate that whatever the battery that I had connected, it would be in the charge condition. I hope you are getting this particular point. Okay, I'll explain this particular concept in depth. Just understand how we are going to design it. Okay, now the second condition is that if I connect the battery whose voltage is less than that, or in general way, if we are considering like the battery, if it is in discharge condition, right? So it won't be able to deliver 9 volt over here, and if it is not able to deliver 9 volt over here, so the voltage drop across base emitter junction, it would be less than 0.7 volts, and it would be operating in the cutoff region. So the second scenario is that if VCC, okay, if VCC it is less than 9 volts, okay, so that means if you are connecting a battery of around 5 volts, so at that particular time, this particular LED would be in the switch off condition. It won't emit any light. Okay, so if VCC it is around, if it is less than 9 volt, okay, and that this same thing you should write. That means if we are providing voltage less than 9 volt to this particular system 1, so what is going to happen? Your VBE would be less than 0.7 volt, right? Your VBE would be less than 0.7 volts, and then your BJT will operate as a open switch, or rather it will be operating in the cutoff region. Let me highlight this particular point. Okay, and let me move this whole of the thing a little bit over here. Alright, so now what is going to happen? Let me just make one line which will indicate that there is a difference between both of these points. Just a second, just give me a minute. Right, so this is your circuit diagram. These are the conclusions, or these are the conclusion that we are deducing. Okay, alright, that means what? Let me move this particular thing little up. Alright, that means my agenda is that if I'm connecting a battery which is less than 9 volts, or rather if the battery it is in discharge condition, so BJT should operate in cutoff region, okay, or it should act as an open switch. Great. So this is the basic understanding. All right, so now that we had got a basic idea or the basic understanding of how we can operate BJT, okay, now what we are going to do, we are going to find out the values for R1, R2 and R3. Okay, what should be the value of R1 and R2 such that if whenever we are providing 9 volts to this particular system 1, so the voltage drop across base emitter junction, it should be 0.7 volts. Okay, and if we are able to provide 0.7 volts to this particular base emitter junction, so a current would be flowing from this particular collector to emitter junction, but at that particular time we need to keep this particular resistor in such a way that there won't be a maximum current that would be flowing through this particular LED. Okay, just to make sure, or just to ensure that this LED won't burn out completely. Okay, so what should be the values of R1 and R2? So this is what we are going to design. Let me proceed further. All right, So I hope you are very much well aware of the voltage divider formula. Let me just just a second, let me just decrease the size of this particular circuit. Oh, sorry, let me just decrease the size of this particular circuit, just a second. All right, and let me show this particular battery. Let me show this particular battery, and as of now we had assumed that whatever the battery that we are connecting, it is of 9 volts. Okay, so you have to keep this particular assumption in mind. Just a second. Right, so this particular battery, whatever the battery that we are connecting, it is in charge condition, and most importantly it is able to provide 9 volt, right? Just a second. Yeah, it is able to provide 9 volts. So let me just show it to you. Okay, plus minus, so this is plus, this is minus, and this is 9 volt of battery. Okay, which is in charge condition. Great. And what we want is that whenever we are connecting this 9 volt of battery to this particular system, so the voltage drop across the resistor R2, or the voltage drop between the base emitter junction, it should be 0.7 volts. So these are the two values that we know. Just a second. So the voltage drop across the base emitter junction, or rather the voltage drop across resistor R2, should be equivalent to 0.7 volts. So the VBE should be equivalent to 0.7 volts. Okay, all right. And I hope you are very much familiar with the voltage divider bias technique, so you might be aware of that particular formula of the voltage divider bias technique as well. Okay, so I'm not explaining that particular formula over here, because that formula we had seen in the course, right? I hope you are familiar with that particular formula. Okay, so what is that particular formula? So the formula is, see, VBE, it is equivalent to, that means voltage V2, and over here V2 is VBE, it is equivalent to VCC, over here VCC is 9 volt, into this particular resistor R2. Okay, R2 divided by addition of both the resistor, that is R1 plus R2. Great. Now you will tell me, sir, that's fine, we have value of VBE, we also have value of VCC, but still we are unaware of R2 and R1. So what should we do in this particular scenario? So my dear student, see, whenever you are unaware of certain values, you have to assume certain things. See, what we had done over here, we had assumed this particular scenario, or rather we want this particular condition. So that's why we assume that this particular battery, it is in charge condition, and at that particular time we are getting this particular voltage. This is what we had assumed, right? And over here as well, since we are unaware of this particular resistor, or rather we are unaware of the values of this particular resistor, so we will consider a general value. Okay, a general value of resistor. So let's assume the resistor R2, it is roughly around 1 kilo ohm. Okay, this is the assumption. Okay, the value of this particular resistor, it is of 1 kilo ohm, and this is what we had assumed. Okay, this is what we had assumed. Okay, this is what we had assumed. Now you will say, sir, why, like, can I assume the value of resistor as 10 kilo ohm? I will say yes, absolutely fine. Can I assume the value of resistor as 1 mega ohm? I will say that is also fine. But again, when you increase the value of resistor, so there might be some heating issues in your circuit, right? And unnecessarily you would be consuming more voltage, right? Okay, so that can create a chaos, right? So remember one thing, whenever you are designing any circuits, and at that particular time when you are assuming certain values of resistor, so you just take these values like 1 kilo, maybe 3.3 kilo ohm, 10 kilo ohm. That would be preferable, because the very first thing is that they are easily available in shop or the market. Secondly, they do not generate that much of heat, or heat dissipation is not that much by this particular resistor, right? So these are the two things you have to keep in your mind. So that's why I took 1 kilo ohm. If you want, you can also take 10 kilo ohm, but surely you don't, please, it's my request to you, please don't go beyond 10 kilo ohms, or maybe 50, 30 if you are taking those values. So it's a very huge value. Okay, and now if you tell me, sir, can I take the value of this particular resistor as 10 ohm, 20 ohm? We'll say no, because we are working at 9 volts, and it's quite dangerous if you are working at so high voltage. I know it's for you all guys, it is, first of all, it is a DC voltage, and it's quite less. you can easily handle this particular voltage. But I'm not talking about you, I'm talking about this particular transistor, this particular LED. So for that very purpose, take values, okay, greater than maybe 1 kilo ohm or less than 10 kilo ohm. Okay, you have to play in that particular range. So that's the reason to take this particular value. Okay, so I'll consider the R2 as 1 kilo ohm. So uh, now that I had got the value of R2, so I can easily calculate the value of R1. So VBE, it is 0.7 volts. Great. So 0.7 volts, which is equivalent to 9 into 1 kilo ohm, that means 10 raised to 3 divided by 10 raised to 3 plus R2, right? 10 raised to 3 plus R1, sorry, not R2, this is R1. So let me just put this value in calculator. I'll shift solve this particular calculation and I will directly put the value over here. Let me just calculate this value. Alright, the value of resistor R1 that I am getting, it is roughly around value of resistor that I am getting, just a second, R1 that I am getting, it is roughly around 11.857 kilo ohm. 11.857 kilo ohm. Okay, so now if you go in market, okay, I mean through the shopkeeper, and if you tell him just give me the value of this particular resistor, that is 11.857 kilo ohm, so he won't be able to give this exact value of this particular resistor. Why? Because there are certain set of resistor, I mean certain set values of this particular resistor. That means you would be able to get 10 kilo ohm, 1 kilo ohm, maybe 1.5 kilo ohm, maybe around 1.3 kilo ohm. So these are the set of resistor, that means 50 kilo ohm, 47 kilo ohm. Okay, but you won't get exact value of this particular resistor from the market. That means you cannot get a resistor of around 11.857 kilo ohm. Okay, so the closest value that is available, it is around 10 kilo ohm. So you would be easily able to get the value of this particular resistor. That means you can consider R1 as roughly around 10 kilo ohm. It's fine because it is very much close to 857 kilo ohm, right? So you can take R1 as 10 kilo ohm. Okay, so let me highlight it. So the value of R1 that I got, it was 11.857 kilo ohm, but I'm considering 10 kilo ohm. Okay, why? Because in market 11.857 kilo ohm of resistor, it won't be available, right? So the closest value, it is around 10 kilo ohm. Okay, you can also take 12.1 k, I think 12.1 kilo ohm of resistor, I think it is available in market. I need to check, but yeah, you can go around 12 kilo ohm to around 10 kilo ohm. So I took 10 kilo ohm. Okay, alright, so we got the value of R1, it is 10 kilo ohm. We also got the value of R2, I mean we had assumed it is 1 kilo ohm, right? Now what about R3? So for that, if you could remember in course, I had clearly mentioned that whenever you are connecting a resistor to this particular LED, okay, I mean in series with LED, so the value of this particular resistor, you need to keep it at around 100 ohms to 500 ohms. Okay, 100 ohms to 500 ohms. Okay, 100 ohms to 500 ohms. Okay, but for this particular application, we will keep the value of this particular resistor as 500 ohms. Okay, I will tell you the reason why I'm not going with 100 ohms. Okay, I will tell you this particular reason when we will simulate this particular circuit on the Proteus software. So just have patience, just wait for it. Okay, so let me write the value. Okay, so just a second, let me see. All right, so the value of resistor R1, it is 10 kilo ohm. So the value of this particular resistor, it is 10 kilo ohm. Okay, the value of this particular resistor R2, it is around, let me just shift this particular R2 over here. Alright, so the value of this particular resistor, it is 1 kilo ohm, which we had assumed. Okay, which we had assumed. Great. Okay, so I hope you understood everything up till here. So basically we are able to design system 1. Okay, so this was our assumption that we are going with the charged battery. Okay, then we had successfully designed system 1, and obviously with the help of system 1 you would be able to get the output as well, that we will check now in the Proteus software. So let me design this particular system in the Proteus software. Alright, so you can clearly see I had designed this particular system in the Proteus software. You can clearly see, just a second, let me go back. Alright, so you can clearly see over here, this is my resistor R1, which is of 10 kilo ohm, this is 1 kilo ohm, and this is R3, it is of 500 ohms. I will tell you the reason why I'm not going with 100 ohms. Okay, all right. So you can clearly see I'm connecting a 9 volt of battery. Okay, this is a switch, you don't worry about it. I will explain you this particular part later on. Okay, this is 500 ohm, this is 10k, this is 1k, and this is your BC547 transistor. Now let me run this particular circuit. Alright, so you can clearly see this LED, it is in the on condition. It is emitting green light, and you can clearly see this is green color LED as mentioned over here, and the voltage drop across the collector and emitter junction, it is 0.53 volts. Okay, so now let's assume if I'm changing the voltage from 9 volts to around 0 volts, 9 volts to around 0 volts, or rather if I change the voltage from 9 to around maybe 5 volts. First of all, we'll see for the 5 volts. So you can clearly see this LED, it is in off condition. Okay, and the voltage drop across the emitter and collector junction, it is around 5 volts. Okay, now let me change the voltage from 5 to maybe 0, and obviously there won't be any significant drop. Obviously over here as well you will get 0 volts because the battery, it is in discharge condition, right? Now just a second, I'll again and sorry, I just failed to explain this particular one. See why I'm designing or why I'm implementing system 2, because over here if my battery, it is in discharge condition, so we are not getting any indication if it is in discharge condition. Okay, although you can since you had designed this particular circuit, so you would be in this situation to understand, since my LED, it is in off condition, or rather my LED, it is not glowing, so this particular battery, it is in discharge condition. But as a user, let's suppose if I buy this particular, or if I purchase this particular circuit from you, so as a user, how I would be able to recognize if my battery, it is, if this particular battery that I had connected to this particular system one, or rather to this particular system, it is in charge condition or it is in discharge condition. For a layman, if this particular, if for the layman, if that particular user connects this particular battery to this particular circuit, and if this particular circuit, if it is in discharge if this particular LED, it is in off condition, so for him it would be like this particular circuit is not working properly. Okay, I hope you are getting this particular point. So for layman, if this particular LED, it is in off condition, so he will think that this particular circuit is not working fine. Okay, but since you are engineer, you had designed this particular circuit, so you would be knowing that this particular battery, it is in off condition, so that's why this particular green LED, it is in off condition. Okay, any which ways, we will come to this particular point that why I had considered 500 ohms over here. Let me just take 9 volts over here. The very first reason is that, see, we don't want maximum current to flow to flow from this particular LED. Okay, we want a minimum of around 10 to 5 milliampere of current to flow through this particular LED. We don't want maximum current, because 20 milliampere of current is the maximum limit, or that is the upper limit. Okay, if you go beyond that particular limit, then this particular LED will burn out completely. So we want minimum current around 5 milliampere, 10 milliampere, that is fine. So that's why we had connected 500 ohms. And the second reason is that, let me just run this particular circuit. See, when I am keeping this 500 ohms, I mean when I'm keeping the value of R3 as 500 ohm, so the voltage drop across the collector and emitter junction, it is around 0.5 volts. It is around 0.5 volts. It is clearly visible to you, I hope. Yeah, you can clearly see it is around 0.5 volts, and the LED, it is in on condition. You can clearly see over here. Okay, let me decrease the size. Let me resize this particular circuit. Alright, so now let me change the value. Let me now change the value of this particular resistor, that is R3, from 500 ohms to, oh sorry, just a second, yeah, from 500 ohms to around 100 ohms. And now we'll see. Alright, so you can clearly see even at this particular time the LED, it is in on condition, but over here we are getting the voltage drop across the collector and emitter junctions, it is roughly around 5 volts. Okay, so we don't want maximum voltage drop between the collector and emitter junction when my LED, it is in on condition. There is one reason for it. We will see that particular reason after some time. Just have patience. Okay, so we saw two reasons. The very first reason was we don't want maximum current to flow through this particular LED, and the second was we don't want maximum voltage drop between the collector and emitter junction when my LED, it is in on condition. Great. Let me pause this circuit. Let me change the value of this particular resistor to 500 ohm. Okay, alright, so now just a second, Okay, so now we had successfully completed this particular three blocks. Now we will focus on system 2. Okay, now what we'll do, we will focus on system 2. Okay, we will design this particular system in such a way that it would be able to indicate, like if my whenever if I connect the discharge battery, so the system 2 should be able to indicate that your battery, I mean whatever the battery that I'm connecting, it is in discharge condition. Okay, so let me proceed further. I just forgot to explain this particular one. Sorry. So let's assume any which ways. I hope you understood through the simulation when we are providing 9 volts over here. So there was a significant voltage drop between the base emitter junction, which was almost equivalent to zero point 0.7 volt. Okay, which is around threshold voltage of BJT, which is around 0.7 volts. And when BJT was getting 0.7 volt across the base emitter junction, so it was operating in the saturation region. That means it was acting as a closed switch. So this is how it will look like, right? And therefore the LED was in the on condition. Why? Because let me just show this particular LED in on condition. So this particular LED was in on condition. Why? Because whatever the current that was being delivered by this particular 9 volt of battery, this was your 9 volt of battery, so it was actually flowing in this particular direction, right? It was actually flowing in this particular direction, that is IC. Okay, so that's why the LED was in on condition. Okay, I hope you're getting this particular point, right? Okay, and over here, if you could remember in this simulation, you can actually go back go back around a minute back. So over here, the voltage that was being available, it was around 0.53 volts, right? It was around 0.53 volts. Okay, now let me erase all of the thing. Oh, sorry, I mean, which was just a second. I can actually, yeah. So let me erase this as well, and even this as well. Let me change the color of LED to around black color. Yeah, and let me erase this as well, and this as well. All right. So now let's assume that I'm connecting a discharge battery, but instead of connecting a discharge battery, I'll consider that I'm connecting a 5 volt of battery. Okay, let me erase this as well. So yeah, I'm connecting a 5 volt of battery over here. So what is going to happen? See, the voltage drop across the base emitter junction, it will reduce, right? It would be less than 0.7 volts. This is what we had seen, right? So it would be less than 0.7 volts. Okay, so therefore this particular BJT will act as if it is open circuited, or it will act as an open switch, right? So whatever the current that is being delivered by this particular battery, it won't flow in this particular direction, right? It won't be able to flow in this particular direction. So therefore current flowing from this particular loop, it will be straight away zero, and therefore this particular LED would be in off condition. Why? Because since the current is zero, so there isn't any significant voltage drop across this particular LED, right? Sorry. So this particular LED would be in off condition. And now in this particular scenario, if you could see at the voltage drop across the base emitter junction, right over here only, it would be quite high. So this particular voltage, it would be high. Whatever the voltage that would be available over here, it would be high. And over here, the voltage that would be available, it would be roughly around 5 volts only. Why? Because you can clearly see there would be certain voltage drop across these 500 ohms. Okay, there won't be any voltage drop across this LED, or there would be hardly any voltage drop, right? So you can clearly see the like the maximum voltage drop, it would be available over here at this particular side. Okay, if you connect multimeter over here, so you would clearly see the voltage drop available over here, it is around 5 volts. Okay, so now over here what you can think is this. Now if I connect a red LED over here, okay, if I connect another LED, so in this particular scenario, what will happen is this. Let's assume if I'm connecting one more LED, let's assume it is red LED. Okay, this is my red LED. If I connect this particular red LED to the emitter side, so now sir, what will happen is that whatever the current it would be generated by this particular battery, it will flow in this particular direction, right? So basically in this particular scenario, what is happening, your red LED will also glow and your green LED will also glow. Okay, so that is the drawback. We don't want both of the LED to be in the on condition at the same time, right? We just want one LED to glow at one time. So if my voltage, it is 9 volts, okay, if my battery it is in charge condition, so this particular green LED should glow, and if my battery it is in discharge condition, so this red LED should glow. Okay, so we need to design a system in such a way that see, to the input side of the system we are getting around roughly around high voltage, okay, high voltage even if the battery is in discharge condition, right? So at the output side of the system as well we should get high voltage, okay, but at that particular same situation this particular green LED should be in off condition, right? So basically, can I say in this way, I'm getting high voltage, that means I'm getting logic 1 to the input side of the system. So at the output side as well it should get logic 1, okay, but in this particular scenario whatever the output that was being generated by the system 1, it should be, it should remain off, or rather it should get logic 0. I hope you are getting this particular point. So basically I'm making use of digital electronics over here. Since I'm dealing with logic 1 and logic 0, right? So let me go to the designing part, okay. So this is how you should design a system. See, if you are getting 5 volts over here plus 5, if you are giving plus 5 volts over here, so over here logic 1 would be available, okay. That means high voltage would be available at this particular terminal of the NOT gate, okay. So that's why I had intentionally used NOT gate. If you want you can also use transistor instead of NOT gate, because NOT gate has one transistor, right? So you can also use transistor, but again, why to use transistor when you have one IC, right? Because in one IC 6 different NOT gates are available, right? So that's why I preferred using NOT gate. So if at the input side of the NOT gate you are getting logic high or logic 1, sorry, so at the output side you will get logic 0, and at the output side you will get logic 1, and therefore this particular red LED would be in on condition. I hope you are getting this particular point, okay. On contrary, I hope you understood this particular scenario. If you don't, please just move back and please watch the video once again, the last 20-30 seconds. Now let's suppose if this particular voltage it is around 0 volt, okay. So now if it is around 0 volts, okay, because the discharge battery provides 0 volts, right? Discharge battery provides 0 volts, okay. So if we are connecting a discharge battery over here, still we would be able to get logic 1. There is one reason for it. I will explain you that particular reason after some time, like when we will simulate this particular circuit. What I'm telling to you, see, in the previous scenario we consider 5 volts over here, okay, but now instead of 5 I'm considering that we are connecting a discharge battery, and we all know discharge battery provides 0 volts, okay. So even though we are providing 0 volts over here, so still we would be able to achieve logic 1 over here. That means we would be getting higher voltage at this particular terminal. What can be the reason for it? It's my request to you, please pause this video and try to think in your mind. I will tell you the reason after some time. Just have patience, okay. All right, but any which ways I hope you understood this particular concept, okay. So let me erase this particular thing, and now if I'm providing 9 volts over here, okay, if I'm providing 9 volts at this particular terminal, so you would be getting logic 0. Why? Because if you could remember during simulation we were getting 0.53 over here, 0.53 volts, which we can consider as 0 volts. So if we are getting logic 0 over here, so you will get 1 over here, logic 1, and over here you will get logic 0. That means what? Whenever you are providing 9 volts over here, so this particular green LED will be in on condition, at this particular red LED it would be in off condition, okay. And whenever you are connecting a discharge battery over here, just a second, let me erase all of the thing. Alright, so now if I am connecting a discharge battery which will obviously provide 0 volts, okay, so this particular LED would be in off condition, okay, but since even though we are providing 0 volts over here, still we will get logic 1 over here, okay. And if we are getting logic 1 over here, we will get logic 0 over here and logic 1 over here, and I will explain you this particular reason. Like even though we are providing 0 volts to this particular VCC, then how we are able to get, or how we are able to achieve this particular logic 1, okay, without including any of the ICs or any of the circuitry, we would be able to gain logic 1 over here, okay. So for that, let me move to the circuit diagram, just a second. Alright, so this is how the circuit diagram will look like. See, over here you will connect VCC, that means charge or discharge battery, you will connect over here. The positive side of the battery you will connect over here, okay, and the negative side you will connect over here, right? Great, okay. And then these are the two voltage divider bias resistor, that means 10k and 1k. You can clearly see over here, this is 10k, 1k, right? This is your VCC, you're connecting positive terminal over here and negative terminal over here of the battery, right? And then through the VCC you have this RC, which is around 500 ohms, right? So this is 500 ohms, right? And to the other end of 500 ohms you have LED. That means this is I'm talking about this particular part, this particular loop, right? And the emitter terminal, it is grounded, so you can clearly see the emitter terminal, it is grounded. And from the collector side, whatever the output that is coming, you are fetching to the inverter, that means the input terminal of the NOT gate. Okay, so this is what you can clearly see over here. Whatever the input, whatever the output that is being generated at the collector side, you are fetching to the input side of the NOT gate. Okay, that means I'm talking about pin 1, right? And then whatever the output that is being generated by this particular NOT gate, you are fetching to the input of the second NOT gate. So this is what you can clearly see over here. Okay, and then whatever the output that is being generated by the second NOT gate, you are fetching it to the red LED. This is what you can clearly see over here. Okay, and then it is grounded. Okay, but my dear student, this was about the ideal case scenario. So over here, this particular two NOT gates were ideal. These two NOT gates were ideal, right? Ideal case scenario. We are dealing with practical NOT gates. So in practical scenario, what we are doing? Just a second. In practical scenario, we need to connect VCC and ground. Okay, I hope you are getting this particular point. So in practical case, we have to connect plus VCC and then we have to connect ground, right? And at the ground, we are providing negative 3.5 volts. You can clearly see to operate this particular IC, the maximum voltage we can provide over here, it is around 5 volts. Okay, we cannot provide more voltage over here. So the maximum voltage we can provide over here, it is 5 volts, but as of now I'm providing plus 3.5 volts over here. Okay, I'm providing plus 3.5 volts over here, and to the ground side I'm providing negative voltage over here. Okay, so if you could see very clearly, just a second, if you could see very clearly, since these three terminals they are grounded, so I can represent it in this way. Since these three terminals they are grounded, so whatever the voltage that is being available over here, so same voltage is being available over here and same voltage is being available over here. So basically at this particular side I am getting minus 3.5 volts, minus 3.5 volts. Okay, and above, like whatever the voltage that is being available, it totally depends on what voltage we get over here. So that's why if you could see very clearly, now I am coming to this particular point. See over here, even though I'm providing 0 volts, see if you could see very clearly, even the battery, it is in discharge condition and still it is providing 0 volts. So over here you are getting 0 volts. Okay, over here logic 1, why I had written over here, this is logic 1. Just a second, let me erase this particular thing. Okay, that's because I'm considering this particular condition. Okay, all right, so this was your ideal case, but over here what we saw in practical scenario, we need to connect this particular battery, I mean VCC and ground, right? So we are connecting plus 3.5 volts to VCC and negative 3.5 volts to the ground, and at the ground we have negative 3.5 volts. So over here, just a second, I will write over here. So over here, whatever the voltage that is being available, it is minus 3.5 volts. Okay, whereas at this particular terminal you are getting 0 volts. Okay, you are getting 0 volts. Okay, and now if you could look at this particular point, see it would be something like this. Just a second. So you have let me change the color. You have 0 volts. Okay, you have 0 volts. So this is your 0 volts, and then you have minus 3.5 volts. So this is your minus 3.5 volts. So you can clearly see from this particular graph that 0 volts I can consider it as logic 1. So this is, I can consider it as logic 1, whereas this particular thing I will consider it as logic 0, and therefore I told you, even though we are getting 0 volts over here, but still it will act as a logic 1. So over here we are getting logic 1. I hope now this particular concept is crystal clear to you all guys. Okay, and since we are able to achieve logic 1 over here, so over here we will be getting logic 0, and over here we will be getting logic 1 or logic high. That means what? We are getting a plus 3.5 volts over here, and therefore since there is a significant voltage drop across this particular LED, it would be an on condition, even though our battery it is in discharge condition, or whatever the external battery that we are connecting over here. So this particular LED would be in on condition. So this was the reason for it. Okay, and now I hope that you understood this particular concept in depth. Okay, so now what I will do, I will simulate the same circuit in the Proteus software. Okay. Alright, so as you can see, I designed this particular circuit over here. So let me bring it little down. Okay, and what I will do, first of all, I will uh, change the voltage from 5 to 9 volts. Okay, so let's assume I'm providing a charge battery, I'm connecting a charge battery which has voltage of around 9 volts. So let me run this particular circuit. Okay, and you can clearly see this is 7404 IC. This is a NOT gate. Okay, and this is a practical IC. Okay, although over here in this particular image you can see this kind of IC over here, but inherently, over here they had not shown, just a second, see, they had not shown this particular pins. Okay, they had not shown this particular pins. Okay, inherently this particular software has assumed that we had connected, just a second, we had connected VCC to this, inherently this particular software has assumed that we had connected VCC to this particular NOT gate, and then we had also grounded this to both of this particular ICs. Okay, I hope you are getting this particular point. Okay, they had assumed, this particular software has assumed that we had connected VCC and ground. Okay, so let me erase this particular thing. All right, so we had connected charge battery. You can clearly see over here, just a second, you can clearly see over here. Yeah, this is 9 volt. Okay, this is your red LED. Let me move this particular circuit somewhere over here. Right, and now let me run this particular circuit. Alright, so you can clearly see over here my green LED, it is in on condition. When my battery, it is in completely charged condition. That means when my battery is around 9 volts, whereas my red LED, it is in off condition. You can clearly see over here. Let me zoom it out, and you can clearly see the values of resistors as well. I had kept the same values. Okay, I had not interchanged anything. Okay, so you can clearly see my green LED, it is in on condition, whereas my red LED, it is in off condition. You can clearly see over here. So let me again realign it properly, and now this particular circuit would be clearly visible to you. Okay, I hope you understood this particular part. Now let me change the voltage from 9 volt to around, let me pause this particular circuit, simulation, and now I am changing the voltage from 9 volts to 0 volts. Okay, enter, and now let me run this particular circuit, and now you can clearly see over here that my green LED, it is in off condition. See, if I'm connecting a discharge battery over here, let me just zoom it out. So you can clearly see this is 0 volts. That means I had connected a discharge battery. Okay, so even though if I'm connecting a discharge battery, this red LED, it is in on condition, and you can clearly see at this particular time the voltage drop across this particular collector ammeter junction, it is plus 3.5 volts, and the reason is quite same. This is the reason for it. The reason is because over here, just a second, this is the reason. See, at the upper side you are getting 0 volts, and at the lower side you are getting minus 3.5 volts. Okay, I hope you are getting my point. So this is what over here, this is what it is happening over here. So at the lower side you are getting minus 3.47, which is roughly around 5 volts, and over here you are getting 0 volts. So basically, let me decrease the thickness. You are getting logic 1 over here, logic 1. So over here you will get logic 0, and over here you will get logic 1. So I hope you really understood the concept and the logic behind simulating this particular circuit or developing this particular circuit, right? But there is one drawback of this particular circuit, and the drawback is that if I open circuit this particular circuit, that means if I'm not connecting any battery, irrespective of the irrespective of whether the battery it is in charge condition or it is in discharge condition, still this particular red LED, it would be in on condition. So let me just open circuit this particular battery. That means, see, you can clearly see I'm not connecting any battery. Okay, I'm not connecting any battery across this particular circuit. Still this particular red LED, it would be in on condition. Okay, so there is one reason behind it, or rather I would say there is one concept behind it. Okay, so you can clearly see even though I'm providing 9 volts over here, the red LED, it would be in on condition, because this particular battery, this particular circuit, it is open circuited, or rather it will behave as if I had not connected any battery over here. Okay, but the moment I switch off, I switch off this particular circuit, so you can clearly see the green LED, it is in on condition. That means the battery, it is in charge condition, and if I switch off this particular circuit, so you can clearly see the red LED, it is in on condition. Okay, but this is the drawback of this particular circuit. Even though I am not connecting any any battery across this particular circuit, still this particular red LED, it is an on condition. Okay, but apart from this particular drawback, there isn't any issue. Okay, but let me tell you, this particular drawback, I mean the concept behind this particular drawback, I will explain you in the next video. Okay, so you make sure to subscribe my YouTube channel to get notification about that particular video. Okay, I'm not explaining that particular part over here. This is because I don't want to increase the length of this particular video unnecessarily. Okay, so that particular video will consume roughly around 15 to 20 minutes. So that's why I just thought that I should make a new video, and then I should explain this particular concept, that why this particular red LED, it is an on condition. So basically this particular parts, you can clearly see these two NOT gates and this red LED. So this particular part I will explain you in the next session, I mean the drawback part. Okay, but apart from that, I really hope that you understood what are the concepts or what are the logic that we had discussed in this particular, or while designing this particular circuit diagram. Okay, so now what I will do, I will just stop this particular video over here, and then I will demonstrate I had actually implemented the same circuit on the breadboard. Okay, so I will demonstrate that particular circuit. Okay, and instead of red LED, I had used orange LED. I didn't had any red LED, so I just made use of the orange LED. Okay, apart from that, I had not done any changes, okay, in that particular circuit. Okay, so just go through that particular video. Okay, and the drawback we will see in the next session. Okay, so thank you for listening patiently. I'm ending this video over here. Thank you. So hello everyone, I had designed this particular circuit to check if my battery is in charge condition or it is in discharge condition. So this particular circuit will only work for the 9 volt of battery. As you can see, this is a 9 volt of battery. Okay, so let's jump to the working part of the circuit. If one of my battery, if my battery is in charge condition, so only this green LED will glow, which is present over here. And if the battery it is in discharge condition, then this green LED won't glow, rather only this particular orange LED will glow. Okay, so let's connect this particular battery and check if it is in charge condition or it is in discharge condition. Alright, so you can clearly see that this particular battery, it is in charge condition, as only this particular green LED is glowing, whereas the orange LED, it is in switch off condition. Okay, so let me disconnect this particular battery and we'll check if this particular battery, it is in charge condition or it is in discharge condition. Just a second. Yeah, you can clearly see that this particular battery, it is in charge condition. Okay, now what I'll do, I'll take another battery and I'll check if this particular battery, it is in charge condition or it is in discharge condition. Okay, so let me connect this particular battery. Alright, so you can clearly see that if I'm connecting this particular battery to the circuit, then the green LED is not glowing, only the orange one, it is just in the switch on condition. So let's check if this particular battery, it is in charge condition or it is in discharge condition. Alright, so you can clearly see that this one is in the discharge condition and this was in charge condition. Okay, this was in charge condition. Okay, once again I will show you. See this particular battery, just a second, this particular battery, it is in charge condition. Okay, so if I'm connecting this particular battery to the to this particular circuit, only the green LED will glow. You can clearly see that only green LED it is glowing. Okay, and the orange LED, it is in switch off condition. Okay, let me disconnect this particular battery, and if I'm connecting this particular battery, the discharge one, to the circuit, so only orange LED is glowing, right? Only orange LED is glowing. Okay,